Okay, today's lesson we are going to determine the equation of an exponential or log function from a table of values, and we are also going to graph log functions. It's just a reminder, you have a quiz on Friday. Take a minute and check your homework from last night. Okay, go ahead and turn to page 33 in your packet. In this student learning task, we are going to explore patterns in tables to determine the type of function that best fits the data, and by hand determine an equation to represent that function. So what I want you to do is examine these two tables, and I want you to think about how are the data in the two tables related, and what type of function do you think fits each set of data. And just for those of you who don't have it, here are the tables. Okay, so hopefully you realize that table 1 is an exponential function and table 2 is a logarithmic function. And one way we can quickly determine that is we see that for table 1, the y values have a multiplication pattern going by 10. So these are multiplying by 10 every time. And over here on table 2, the x values have a multiplication pattern. And since the log is the inverse of an exponential, this is our exponential function, and this is our log function. Okay, so next question I want you to consider. How can we use a table? Well, we just answered those questions. If it's got a multiplication pattern on the y values, it's exponential. If it's got an multiplication pattern on the x values, it's logarithmic. So let's take a look at determining these functions. So it appears that table 1 is just straight up 10 to the first is 10, 10 squared is 100, so its function is simply going to be y, or in this case h of x equals 10 to the x. I guess it's h of x that says that on the top of the table. Now, the second table for m of x, table 2, it's just straight logs. So for example, right here, if we have an input of 100, log base 10 of 100 is just 2. Log base 10 of 1,000 is 3. No transformation, just straight log base 10 of x. So go ahead and turn to page 34. On page 34, we see two additional tables. Take a second and consider if each is logarithmic or exponential. Okay, so hopefully you saw for table 3, we kind of have a multiplication pattern going on. It almost looks like we're multiplying by 10, but then there's something else that happens. So let's think. If we had 10 to the first power, what would we have to do to get 8? And if we had 10 to the second power, what would we have to do to get 98? And 10 to the third power, what would we have to do to get 998? And if you said subtract 2, you're correct. So that means that p of x is going to be 10 to the x minus 2. Not such a big deal. So when we look at table 4, we know it's logarithmic because clearly there's some kind of multiplication pattern going on with the x's. That tells us it's logarithmic. So the problem is if we've got log base 10 of 1, what does that give us? 10 to what power gives us 1? Well, 0. Wait a minute. Okay, so I just discovered a mistake in this county worksheet. Guys, everybody change where it says x is 1, make that a 2. Okay. So if we have log base 10, we can kind of tell they're multiplying by 10. The problem is that log base 10 of 11 is not 1. Log base 10 of 10 is 1. So think, what do we need to do to all of our arguments? So here we've got log base 10 of 101, and we want our answer to be 2. What do we have to do to the 11 and the 101 and the 1001 so that the output will be 1, 2, 3? Well, if you said we need to subtract 1, you're correct. So like if we have log base 10 of 1001 minus 1, that would be log base 10 of 1,000, which is 3. Make sure you make that change. That should be a 2, not a 1. Okay, and so our function is just going to be log base 10 of x minus 1. Again, I really can't emphasize enough, once you think you have your function, it's important to go ahead and check it. So like log base 10, 10,000 minus 1, or 10,001 minus 1 would be 10,000, and then that's 4. All right. Go ahead and take a look at page 35 and pause the video and try those two on your own. Okay, so when you looked at table 5, hopefully you noticed that you've got a multiplication pattern on the x's. It's a little tricky because, you know, they're not perfect. So let's think. We know that to get rid of the 5/3, we probably had to multiply by 3 to get rid of the third. So let's see what happens. If we multiply by 3, that would give us -5. Okay, so we know that we have a multiplication pattern here of multiplying by 3 because otherwise there would be no way to get rid of this fraction. So let's think. 3 to the first would be 3, and it's supposed to be a 1. 3 squared would be 9, whoop, and it's supposed to be a 7. So what do we have to do with all of these values? So similarly, guys, 3 to the -1 would be 1/3. 3 to the 0 would be 1. What do we have to do to all of these values to get the output values? We have to subtract 2. 9 minus 2 would be 7. 3 minus 2 would be 1. Let's test it with one of the ones down below. So let's test it with 4 because that's my favorite, 3 to the 4th. So if I do 3 to the 4th minus 2, 3 to the 4th is 81, minus 2 would be, check, 79. And sure enough, there it is. Now, taking a look at table 6, b of x, the b values are going up by 1, and there seems to be some kind of multiplication pattern here. So again, I'm starting here with a fraction, and it's 3/2, and all of a sudden the fraction is gone. So to get rid of that, 3 divided by 2, I probably had to multiply by 2 going down. So let's think. If we're multiplying by 2, if that's the pattern, what's 2 to the 0? 2 to the 0 is 1. But there's a 2 here. So if this is going to be my argument because it's going to be log base 2 of something. And I know that this is my exponent, 2 to the 0. I need to make this my argument so that I would, want to produce this exponent. The argument here really needs to be 1. So let's think. If I have log base 2 and there's a 2 here, and I got to do something so I get a 0 here, well, log base 2 of 2 would be 1. And it's supposed to be 0. But if I take the 2 and subtract 1, log base 2 of 1 gives me 0. If we've got log base 2 of 3 minus 1, that would be log base 2 of 2. Yep. If I've got log base 2 of 5 minus 1, that would become 4. 2 squared is 4. Yep. So again, what I did is once I realized the multiplication pattern had to be multiplying by 2, I wrote log base 2 and I put my argument here, my 2. But then the problem is log base 2 of 2 wouldn't give me this 0, it would give me a 1. That's not what I want. So I had to think, what would I have to do to my 2 so that log base 2 of whatever would give me 0? Well, I know that log base 2 of 1 gives me 0, so I took the 2 and added the little minus 1. And then down here, I need to have an output of 1. Log base 2 of what gives me 1? 2. So I changed the 3 to 3, and that still works. 3 minus 1 is 2. So our final b of x for table 6 is log base 2 of x minus 1. I mean, you guys can check this all the way down. Here I've got an output of 4. I know the multiplication pattern is 2. This is a 17. Okay, that is not a power of 2. 2 to the 4th is how much? 16. So I need this argument to be a 16. So again, the -1 still works. What I want everyone to do is to flip over to, there's a blank page on page 36. And I want everyone to please write down number 1 that you see here on page 36. Okay, so unfortunately, this curriculum just kind of expects you, once we've graphed a log function, to just magically be able to graph these transformations, and we know that that's just not how the world works. So before I send you off on your own to do 37 and 38, on page 36, we're going to do 3 graphs together. Well, we're going to do 2 graphs together, and then you're going to do one by yourself, and we'll check it. So write down number 1. Now, we're still going to approach this the way we did when we had the parent graphs. What we want to do is we want to have this argument equal powers of 2, because that's the base. Okay, so write that down. We want the argument, we're going to set the argument equal to powers of 2. So the first thing I'm going to do is I'm going to say that x minus 4 equals 0, which is not a power of 2. But I know I can't have an argument equal to 0. I can't take log base 3 of 0. So I know that whatever x value results from this, this is going to be, because it really can't equal 0, my asymptote. Okay? Now, 2 to the, 3, oh, whoops, why am I saying powers of 2, stupid? It should be powers of 3, sorry. I don't know, I had a moment there. Maybe I was looking at number 2. So, 3 to the 1st, 3 squared. That's probably enough. Oh, I forgot 3 to the 0. That was silly. Let's change these. We'll make that one a 3. We'll make this is 3 to the 0. Which is 1. This is 3 to the 1st. And then we'll do one more, 3 squared, x minus 4 equals 9. So now everyone go ahead and solve your cute little equations. We get x equals 4. We get x equals 5. We get x equals 7. And we get x equals 13, which is too big for our graph, so oh well. So these are the x values I'm going to put in my table, except for the first one. I know the asymptote is x equals 4 because I can't have an argument of 0. So I'm going to go ahead, write it away, and put in my dotted asymptote at x equals 4. Okay. All right, now I'm going to make a table of values. And the 3 numbers I'm going to put in for x are going to be 5, 7, and 13. So what I'm going to do now is I'm going to go back to my x equals 5, log base 3 of 5 minus 4 plus 5. So 5 minus 4 is 1. Log base 3 of 1. Well, 3 raised to what power gives us 1? That's 0. 0 plus 5 gives us 5. So the first point I'm going to graph is going to be 5, 5. Then I'm going to go to 7. And I've got, so here's the x equals 7 that I got from that argument. Log base 3 of 7 minus 4 plus 5. 7 minus 4 is 3. 3 to what power gives me 3? 1. 1 plus 5 is 6. So I'm going to graph 7, 5, 6, 7. Now, 13 is way off my graph. I'm going to evaluate it just for funs. So log base 3, 13 minus 4 plus 5. So 13 minus 4 is 9. 3 squared gives me 9. So 2 plus 5 is 7. So somewhere over here, there's like a point. Now what I can do is I can graph my curve. So it comes up from the asymptote, it's 3, so that's a growth. Plus I can tell this is the asymptote, I have a point here, I have a point here, I have a point here. Clearly, it's gonna have to come up. All right, and there's my graph. My domain is gonna be x, ooh, I don't know why that's 0. I'm having a morning, not enough coffee. Is gonna be x is greater than 4. The range is going to be all real numbers. Okay, so what I want everyone to do, number 2, we need powers of 2. I need to do a little erasing here. So we're going to do the same thing we did for number 1. We're going to take the argument. We know the argument cannot really equal 0. That will be my asymptote. So that tells me I have an asymptote at x equals -1. Can't have the argument equal to 0. Can't raise 2 to the power and get 0. So now 2 to the 0 power would be 1. And then 2 to the first power would be 2. And 2 to the second power would be 4. All right, so now I'm going to go ahead and solve these real quick. I get x equals 0, I get x equals 1, and I get x equals 3. So those are the 3 values that are going to go in my table. 0, 1, and 3. And I'm going to go ahead and evaluate these now. And I'm just going to go plug them into the original equation. I've got negative log base 2 of 0 plus 1 plus 6. Now I'm going to evaluate this slowly and then I'll erase it and do the next one. So 0 plus 1 is 1. 2 raised to what power is 1? 0. So it's almost like I have negative 0 plus 6. So I have the point 0, 6. I'll put my asymptote in. Okay, so now I'm going to grab my eraser. Alright, so now I'm going to put my next number in, which is 1. So I've got 1 plus 1 is 2. 2 to what power gives me 2? 1, but it's negative. So I've got negative 1 plus 6 is 5. So now I'm going to put 3 in. Put the 3 in. So let's see. 3 plus 1 is 4. 2 to what power gives me 4? 2. But there's a negative, so it's really negative 2. Negative 2 plus 6 is 4. I cannot emphasize enough that you need to show all this arithmetic, or you are just going to make so many careless errors, it's going to be very sad. Once I have my 3 points, I can see that my curve is coming down from the asymptote, which makes sense because I got this negative in front, which is a reflection over the x-axis. And I'm going to come down. My domain is going to be x is greater than -1. My range is going to be all real numbers. I want everyone to write down number 3. And I want you to try it on your own. I'm going to work silently, so don't look up until you're done. Don't get nervous about the fractions. So we've got log base 3. Oh, sorry, I said I wasn't talking. Nine, 3, base 3 of 3. Just gonna slide this down to do my arithmetic. You better have all your arithmetic shown, or it's gonna be sad if you get it wrong. Good mathematicians show all their arithmetic when they're dealing with something that's not straightforward. 15. Okie dokie. So everyone take a second. Make sure you've got the x values to go into your table correct. Then I put them in my table. The 7/3 weirded me out a little bit, but then I remembered I was going to multiply by 3, so it was a no worries situation. So I'm going to graph my points. So 7/3 is like a little more than 2, but a little less than 3, because 9/3 would be 3. So it'd be like here and -4. Then we've got 3, -3, and we've got 5, -2. So I can see that this one comes up from the asymptote based on the 3 points. But I just have that little fractiony one. It's not weirding me out too much. Oh, that's a terrible looking curve. Sorry, guys. Okay. My domain is going to be x is greater than 2, and my range is going to be all real numbers. So go ahead and turn to page 37 and get started on your homework. Your homework tonight is 37 and 38. I have the answers in this video, and I will show them shortly. So everyone go ahead and get started on those two. The KP, just so you see this here, Miss Weiss calls those the key points. I like to make tables. She likes to write ordered pairs.